An explosion rips through a port city. A skyscraper suddenly collapses into a cloud of dust. A submarine vanishes without a trace in the deep ocean. These are catastrophic events that capture the world's attention. While investigators pore over satellite images and eyewitness reports, some of the most crucial evidence comes from an incredibly powerful and unexpected witness: the Earth itself. Welcome to the world of forensic seismology, the science of listening to the ground beneath our feet to uncover human-made secrets. For decades, scientists have studied the Earth's vibrations to understand earthquakes and our planet's inner structure. But starting in the mid-20th century, a new application emerged, born from the need to distinguish the seismic whisper of a secret nuclear test from the roar of a natural earthquake. Today, this science helps us investigate everything from industrial accidents and building collapses to meteorite impacts on other planets. This is the story of how the Earth became a silent witness, its vibrations a permanent record of our most powerful and sometimes most destructive actions. At the very heart of forensic seismology is the study of seismic waves. These are pulses of energy that travel through the planet whenever there's a sudden release of energy, like the snapping of a tectonic plate. Think of it like dropping a rock into a pond, but instead of ripples on water, these are waves traveling through solid rock. The first and fastest waves to arrive at a seismic monitoring station are called P waves or primary waves. They are compressional waves, just like sound waves. They travel through the Earth by pushing and pulling the rock in their path, compressing and decompressing it. P waves can move through solids, liquids, and gases. Following them are the slower S waves, or secondary waves. These waves are different. They move the ground up and down or side to side, perpendicular to their direction of travel. A key detail about S waves is that they can only travel through solid material, not through liquids like the Earth's outer core. Finally, you have surface waves, which are trapped near the Earth's surface. They are the slowest of all, but are often the most destructive during an earthquake because they cause the most ground shaking. There are two main types: love waves, which shake the ground horizontally, and Rayleigh waves, which have a rolling motion, similar to waves on the ocean. Now here is the crucial part for a forensic seismologist. An earthquake, caused by the shearing, sliding motion of a fault, generates a complex mix of all these waves, particularly strong S waves and surface waves. But a human-made event, like an explosion, is fundamentally different. An explosion is a point source that pushes energy outwards in all directions, like an expanding balloon. This creates a much simpler wave pattern, dominated by powerful P waves and very weak S waves. It's this fundamental difference in the seismic script that allows scientists to read the story of what happened. The entire field of forensic seismology essentially began as a geopolitical necessity during the Cold War. As the United States and the Soviet Union engaged in a nuclear arms race, they conducted tests underground. It soon became clear that these powerful explosions created seismic waves that could be detected thousands of miles away. This discovery was a game changer. It meant that nobody could test a large nuclear weapon in secret. This laid the groundwork for a global network of sensors and the birth of a new science. The pinnacle of this effort is the Comprehensive Nuclear Test Ban Treaty, or CTBT, which opened for signature in 1996. The treaty prohibits all nuclear explosions, for any purpose. To make sure everyone is playing by the rules, the treaty organization established an incredibly sophisticated verification system called the International Monitoring System, or IMS. The IMS is a global network of 337 monitoring facilities spread across 89 countries, designed to detect any nuclear explosion anywhere on Earth, underground, underwater, or in the atmosphere. This network uses 4 complementary technologies. First, and the backbone of the system, are the seismic stations. There are 170 of these stations constantly listening for shock waves traveling through the Earth. Second, there are hydroacoustic stations. 11 of these facilities listen for sound waves traveling through the oceans. They use underwater microphones, called hydrophones, to pick up the signature of an underwater blast. Third, 60 infrasound stations are scattered across the globe, listening for ultra-low frequency sound waves in the atmosphere that are far below the range of human hearing. These would be generated by an atmospheric nuclear test. And finally, the fourth technology provides the smoking gun. 80 radionuclide stations act like planetary-scale Geiger counters, sniffing the air for radioactive particles and noble gases that would provide definitive proof of a nuclear explosion. The main job for seismologists working with the IMS is to sift through the data from thousands of natural seismic events that happen every year to find the one that might be a clandestine nuclear test. They have a toolkit of techniques to do this. The first and most powerful tool is comparing the size of the P waves and S waves. As we discussed, an underground explosion radiates energy outwards, creating strong P waves but weak S waves. An earthquake's shearing motion, however, creates very strong S waves. So, if an event shows a high ratio of P wave to S wave energy, it's a major red flag for an explosion. Another key clue is depth. Earthquakes can happen at various depths, from shallow to hundreds of kilometers deep inside the Earth's mantle. But human-made explosions, whether for mining or a nuclear test, have to be conducted at or very near the surface. You simply can't drill a hole hundreds of kilometers deep. So if a seismic event is located deep within the Earth, it is almost certainly a natural earthquake. Finally, scientists analyze the waveform itself. An explosion causes an initial push outwards in all directions. This means every seismic station that detects the event, no matter where it is, will first register a compressional motion, away from the source. An earthquake is more complex. Because of the sliding fault, some stations will register a push, while others register a pull towards the event. This pattern creates a unique fingerprint that can be visualized in what seismologists call beach ball diagrams, which graphically show the type of faulting. A perfect real-world application of this toolkit is the monitoring of North Korea's nuclear program. All 6 of its announced nuclear tests between 2006 and 2017 were instantly detected by the IMS network. The data was unambiguous. The seismic signals showed all the classic hallmarks of an explosion: very strong P waves, weak S waves, and a very shallow depth. This allowed scientists to confidently identify them as nuclear tests and even estimate their explosive yield. While hunting for secret bombs is what started it all, the applications of forensic seismology have expanded dramatically. The same principles can be used to investigate a huge range of other events. Take large chemical explosions. While not nuclear, a massive industrial blast can release enough energy to generate significant seismic waves. A tragic and powerful example is the 2020 Beirut port explosion. When a huge stockpile of ammonium nitrate detonated, it devastated the city. The blast was recorded by seismic stations across the region. By analyzing the data, scientists were able to calculate the event's equivalent earthquake magnitude, around 3.3, and estimate the explosive yield at somewhere between 0.8 and 1.1 kilotons of TNT equivalent. This seismic data provided crucial, independent information to understand the scale of the disaster. The science can also be used to understand why buildings fall. The catastrophic collapse of a large structure, like a skyscraper or a bridge, generates its own unique seismic signal. One of the most somber examples is the collapse of the World Trade Center towers on September 11, 2001. Seismographs around New York City recorded the signals from the initial aircraft impacts, but the subsequent collapses of the towers generated much larger seismic signals. The collapse of the North Tower registered as a magnitude 2.3 earthquake. Analyzing these waves helped investigators create a precise timeline of the tragic events of that day. In another case, during the 2011 Christchurch earthquake in New Zealand, a building called the Pine Gould Corporation building collapsed, killing 18 people. Forensic analysis of the seismic data from the main earthquake, combined with computer models, helped engineers understand exactly how the building failed. The data showed that the collapse was triggered by the failure of the building's central shear core, a critical structural component. The reach of forensic seismology even extends beneath the ocean surface to investigate maritime disasters. Underwater explosions create a very specific acoustic signature known as a bubble pulse. When an explosion happens underwater, it creates a large bubble of hot gas. This bubble expands, then collapses under the pressure of the water, then expands again, oscillating as it rises. This oscillation sends out a series of pressure pulses that can be detected by hydroacoustic stations. The sinking of the Russian submarine Kursk in the year 2000 is a textbook case. On August 12th, seismic stations recorded two distinct events from the Barents Sea, separated by 135 seconds. The second, much larger event was detected as far as 5,000 kilometers away and had the characteristic bubble pulse of a massive underwater explosion. By analyzing the data, investigators concluded that the first event was a smaller explosion, likely from a faulty torpedo, which then led to the second, catastrophic detonation of several of the submarine's warheads. This seismic evidence was key to understanding the sequence of events that doomed the 118 crew members. Incredibly, the reach of this science is now interplanetary. The same instruments we use to listen to our own planet are now listening for echoes from the cosmos on other worlds. NASA's InSight lander on Mars carried a highly sensitive seismometer. Between 2020 and 2021, this instrument detected the faint seismic waves from 4 separate meteorite impacts. Scientists were then able to use the Mars Reconnaissance Orbiter to take pictures of the surface and find the brand new craters that matched the seismic data. This confirmed that they were indeed detecting meteor impacts, giving them a new way to measure how often Mars gets hit. This is crucial for understanding the age of the Martian surface and its ongoing evolution. So what does the future hold for forensic seismology? The field is evolving fast. One of the biggest advances is the use of machine learning and artificial intelligence. Global seismic networks generate an unimaginable amount of data every single day. AI algorithms can now sift through this data in near real time, automatically flagging and classifying events of interest much faster than a human ever could. Another exciting development is citizen seismology. Networks of low-cost, amateur-run seismographs are popping up, especially in urban areas. This provides a much denser web of sensors, allowing for detailed study of smaller, local events that the bigger global networks might miss. Of course, challenges remain. For nuclear monitoring, there's a constant concern about evasion techniques. For example, a country might try to decouple a test by detonating a device inside a massive underground cavern to muffle the seismic signal. Or they might try to mask a test by detonating it at the same time as a large conventional explosion at a nearby mine. Scientists are constantly working on more sensitive methods to counter these potential threats. Looking ahead, forensic seismology will become an even more vital tool in disaster response, helping to rapidly assess the scale of earthquakes and landslides. It also has potential applications in law enforcement, where geophysical techniques can be used to find buried evidence. From the heart of a nuclear blast to the collapse of a building, and from the depths of the ocean to the surface of another planet, forensic seismology gives us a unique and powerful window into our world. By learning how to listen to the vibrations of the earth, we can uncover hidden truths, hold nations accountable, and piece together the final moments of terrible tragedies. The ground we stand on is more than just rock and soil. It's a meticulous record keeper, a silent witness, and its testimony is there for anyone who knows how to listen.